Have you ever really stopped to think about how a video from literally the other side of the planet finds its way to the specific phone you're holding in your hand? It's not magic, I promise. It's all thanks to a hidden system of addresses. And today, we're going to pull back the curtain and see exactly how it works. Let's dive in.
I mean, really, think about the scale here. Billions, zillions of devices all connected at the same time. Laptops, phones, servers, you name it. So how does one tiny packet of data navigate that absolute chaos to find you and you alone? Well, it's all because of an incredibly elegant addressing system. All right, so to wrap our heads around this, let's use an analogy we all get. The easiest way to think about the internet is like a gigantic worldwide postal service. And just like with snail mail, if you want something to get delivered, every single house needs its own unique address. No exceptions. And that's exactly what an IP address is. It's the digital version of your home address. It tells the network's mail carriers, the routers, exactly where to drop off the data so your cat videos don't accidentally end up on your boss's computer. So what does one of these digital addresses actually look like? Let's crack it open and see what makes it tick. Just like your physical address has a city and then a specific street, an IP address has two key parts that work together to find any device online. Let's grab an example here, something like 148.75.0.0. At first glance, it just looks like four numbers separated by dots, right? Kind of random. But trust me, hidden inside those numbers is a brilliant two-part structure that brings order to the entire internet. So every IP address has two main jobs. The first part is the network ID. You can think of this as the zip code and city. It gets the data to the right general neighborhood. The second part is the host ID. That's the specific street address and house number that says, deliver it right here. Now, obviously, not all networks are the same size, so the early internet pioneers came up with a system of classes. Class A addresses are for the giants. Think huge international companies. Class B, like our example, is for medium to large places like universities. And Class C is for smaller local networks. You can tell which is which just by looking at that first number. But this system created a whole new headache. What happens when your zip code, your Class B network, is the size of a massive city? You can't just have one big open space. You need to organize it. You need to create digital neighborhoods. Seriously, can you imagine trying to deliver mail in a city with over 65,000 houses but no streets? It would be pure chaos. In the digital world, this means every piece of data screams at every single device. It's incredibly slow, it's inefficient, and it's a huge security nightmare. And this is where our hero of the story comes in. Subnetting. It's this brilliant technique that's like drawing neighborhood boundaries inside our digital city. We take that one big, messy network and we slice it up into smaller, much more efficient subnetworks, or as we call them, subnets. So how does this work? It's really clever. Remember that host ID part of the address, the part meant for specific devices? Well, we basically borrow a few bits from it. We repurpose them and say, okay, you're not for a specific computer anymore. You now represent a brand new subnet ID. We've just created a third layer to our address. Okay, so we've got this slick new three-part address. But how does a router, the postal worker of the internet, actually use this information? How does it make that split-second decision of where to send the data? This is the data plane in action, and it all comes down to one very special tool. That tool is called the subnet mask. You can think of it as a secret decoder ring for the IP address. A router gets a packet of data, it looks at the IP address, and then it uses the subnet mask to figure it all out. The mask tells it exactly how to read the address. This part is the main network, this part is the subnet neighborhood, and that part is the specific house. The process itself is just some super fast digital logic. The router takes the IP address and the subnet mask, performs a quick mathematical comparison on them. Think of it like laying a stencil over the address, and poof, it instantly isolates the subnet ID. Now it knows exactly which neighborhood the packet needs to go to. And once it knows the subnet, what does it do? It checks its cheat sheets, which is called a forwarding table. It's a super simple map that just says, hey, if a packet is for this subnet, send it out of physical port number 1. If it's for that subnet, send it out port number 2. It's that simple. All right, let's watch this happen in real time. A packet comes in, its destination is 192.10.10.50. The router does its quick math and figures out the subnet is 192.10.10.48. It scans its table. Interface 1, nope. Interface 2, not a match. Interface 3, bingo. And just like that, in a fraction of a second, the packet is forwarded out that port and continues its journey. So that's the theory. And it's pretty cool, right? But to really, really get it, there's nothing better than actually doing it ourselves. So let's roll up our sleeves and get our hands dirty. We're going to design a network from scratch.
Okay, here's our mission. We've been given the network 192.10.10.0. The job is to carve this up into at least 14 separate neighborhoods, and each of those neighborhoods needs to have room for at least 14 devices. Let's walk through it.
First things first, how many bits do we need to borrow? Well, we need 14 subnets, and in networking, it's all about powers of 2. So let's see. If we borrow 3 bits, 2 to the power of 3 is 8. Nope, not enough. So let's try 4 bits. 2 to the power of 4 is 16. Perfect. That covers our 14 and even leaves us with a couple of spares.
Okay, so we're borrowing 4 bits. What does that do to our subnet mask? The first 3 numbers are easy. They stay 255. For that last number, we just add up the values of the first 4 bits we borrowed. That's 128 plus 64 plus 32 plus 16, which adds up to 240. And there it is, our shiny new custom subnet mask, 255.255.255.240.
And look at the result. This is what we've created. We took that one big, chaotic network and turned it into 16 neat, perfectly organized subnets. Each one has its own network address, its own specific range of addresses for devices, and even its own broadcast address for announcements. It's order from chaos. So let's just zoom out for a second. With just a few simple rules and a little bit of binary math, we brought structure, speed, and security to our digital space. And that is the hidden genius of the data plane. This elegant logic that lets routers make billions of lightning-fast decisions every second all across the globe. You know, what's incredible is that this system was designed decades ago, and it is scaled remarkably well, but the internet is just growing exponentially. It makes you wonder, right? As we start connecting trillions more devices, everything from our cars to our coffee makers, what new, elegant systems of logic will we need to invent to keep it all working? What will the internet's address book look like 20 years from now?